Bismillahirrahmanirrahim. In this video, I'm going to talk about the half-life and the unit of the radioactivity. So basically, the radioactive decay is the mark of instability of any nucleus, and half-life is taken to be time, maybe in seconds, minutes, hours, and years, depending on the amount of the radioactivity that is needed for one half of its present amount to disappear or decay. So these are the two graphs I have shown over here. So the first thing is in this graph, there is a plot of radioactivity versus time, and you can also plot the number of radioactive nuclide against time. So the equations are, these are the two equations which are given over here. These are similar. One is is given with the number of nuclide, that means the radioactive nuclide, and in other equation, a T is the activity, or you can say this is the total activity or the total radioactivity. So actually all the nuclides are following the first order kinetics, and these are the equation for the first order kinetics. And here I'm not going to talk about the kinetics, but here to explain the half-life by using these equations. So the first is, if you have a look on this graph, so this is the graph between radioactivity versus time, and you can have a look at this graph. This is exponentially going to decrease, and the reason is over here because there is the relationship between the activity and the time is having the exponential relationship, exponentially decreasing. So this negative sign is going to show you the decreasing, but it is decreasing exponentially. And the same behavior is here. The number of nuclide versus time, it is going to decrease exponentially. So what does exponentially mean over here? And this is the actually the very important description of the first order kinetics, or to calculate or to determine the half-life of the any of the radioactive nuclide. So exponentially mean what is the outcome coming out from this graph, that is the one of the important application of the exponential curve. So this is the exponential curve which is shown over here, and the reason behind this one, because this is following this equation, and this equation is having the exponential relationship between the activity and the time, and that's why you are going to get the exponential relationship or exponential graph. And what does this mean? And you are getting from this explanation, that means how to get the half-life of the radioactive nuclide. So the first, starting with this graph. So what is the half-life? Let's suppose this is the initial activity, the initial activity of any of the radioactive nuclide. And when you divide by 2, that means when the initial activity becomes half, and what is the at, let's suppose this is the initial activity, this is the activity divided by 2, that means when the initial activity become halves, and when you get the time is here, and let's suppose this is the time, this time is called the half-life of the radioactivity. So simply when the initial concentration or the initial activity, here the proper word is the activity, not the concentration, because we are not using the chemical reaction. This is the nuclear activity, so better to use the term activity or the number of the radioactive nuclide. So when the initial activity becomes half, the time at this, that is called the half-life. So now if you want to get the further half-life, now let's suppose this is your initial activity, and when you further half this one, a divided by 2 divided by 2, that means this is a divided by 4. This is the further half of this activity. Then at this time the half life is this, that means this is the 2x. X is mean any of the value over here, it may be 10. Then 2x mean it is a multiple of 10, that means it should be the 20. And when you further half this one activity, a divided a by 4 divided by 2, this will be a divided by 8. And the time at which this is called, also called the half-life. And this is the multiple of the this, because this is the third half-life. And now what is uh, the half-life you can get out of this? Let's suppose this is the 10. From here to here the half-life is 10, and this is the multiple of this 10. That means that's why it is written over here is the 2x. That means 2 multiplied by 10, that is the 20, and this would be the 30. So if you subtract 2x minus x, that would also give the value of x. That means 20 minus 10, that would the value of 10. And this 30 minus 20, this will also give you the value of 10. So that is the actually the property of the exponential curve. In any of the half, you will get the same half life, and this is the actually the importance of the exponential curve. You will not get this behavior from other graphs, and that's why you are getting the half life from this exponential curve. So again, that's why it is written over here. This is the half-life. This is also half-life. This is also half-life. So you can get the half-life from any of the half of the initial concentration, or from here to here, or from here to here. You will get the same half-life, because this is the first order kinetics, and you can represent how to get the radioactivity after n number of half-life. A divided by 2n. If it is 1 first half-life, that means a by 2 as given over here. Or if it is the second half, that means this is n is 2, 2 multiplied by 2, this is the 4, 8 divided by 4. And when it is third half, that means 2 having the power 3, and this will give you the power of the value of 8. So simply you can use this representation, or you can just simply use by understanding this is first half, and then you can further half, when then you can further half, and in each of the half life will remain the constant. That means this is the first order kinetics. Half life is not going to change even you are changing the initial concentration. There is no change in the half life. Half life is independent on the initial activity, and this is the property of the first order kinetics. And one practical example is given over here, how to get the half-life. And now this is the example of the number of radioactive nuclide carbon 14. If you want to get the half-life of the carbon 14, just plot the number of radioactive nuclide versus time. This is the initial number of radioactive nuclides, and whatever is the number over here, when this number is remains half, that means half of the initial, then you can get the half-life from this time, and the half-life is 5730 years. This is the first half-life. When you further half this one, then you will get the value over here, and you want to get the half-life, just extrapolate the curve, go to the x-axis. This will give you the value of the 11460. That means the multiple of the this one, this is the double to this one, because the half-life you are getting the half. Now, if you want to subtract this minus this, you will get the same value 57300. And similarly, if you further half this one, you will get the half-life from the over here from the x-axis. The value is 17190. This is the third half-life, and when you subtract this minus this, you will get the same half-life. So this is the actually this is the half-life of the carbon 14. So half-life is not going to change even you are going to change the number of the radioactive nuclides. Half-life will remain the same. This is the property of the first order kinetics, or the actually the property of the all the radioactive nuclides which are going to follow the first order kinetics. So this is the way you can get the half-life of the radioactive nuclide, and I have explained over here what is the half-life. Now moving to the unit of the radioactivity. Basically, we use the three units. This is the Curie Becquerel disintegration per second. So this is the first is the very simple understanding, and this is the standard unit of the radioactivity, which is measured in Curie, and the symbol is capital C, which is defined as the quantity of the radioactive substance able to produce 3.7 exponent 10 disintegration per second. Actually, this is the rate. You know, rate is the change per unit time, and this change is because this is a radioactive nuclide. This is going to disintegrate, and disintegration per second, and this is called the rate of the radioactive nuclide. And if the value is 3.7 exponent 10 disintegration per second, this is called the Curie. So 1 Curie will be equal to 3.7 exponent 10 disintegration per second. So you must remember what would be the unit of the radioactivity. So sometimes we will use milli and micro Curie or the nano Curie, and these are used to represent with exponent minus 3, minus 6, exponent minus 9 parts of the Curie unit as defined in this. So similarly, you can, as per the radioactivity, you can use the low unit or the higher units. So this is important. The SI unit of the activity is Becquerel, and we represent in the BQ, capital B, small q, since 1975. So it is said to be one nuclear transformation per second. That means one nuclear disintegration per second. So this is called the Becquerel. So when it is 3.7 disintegration per second, or you can say 3.7 exponent 10 becquerel per second, so transformation per second, and this is equal to the becquerel. So 3.7 disintegration per second, or you can say 3.7 exponent 10 becquerel, because one becquerel is the disintegration per second, or the one nuclear transformation per second. Nuclear transformation is the same as the disintegration per second. So that means if one Curie is 3.7 disintegration per second, and one becquerel is actually the disintegration per second, so one Curie will be equal to 3.7 exponent 10 becquerels. This is the, you can represent in Curie or in disintegration per second or in the becquerel. So one Curie will be equal to this becquerel, or you can calculate the becquerel. That would be 1 divided by 3 exponent 10. That will give you the value in becquerel. The becquerel is simply in the nuclear transformation per second or the disintegration per second. That is the one disintegration per second. This is the becquerel. Now, these are the units as per your convenience. This is just the table because in the previous slide we used the milli, micro, or the nano with the power of this. So 1 milli, 1 micro, 1 nano equal to how many the units are there, but these are the measurement. You can represent over here the Curie. So similarly, you can use the higher units or the lower unit factor as per your convenient, depending on the radioactivity. This is the last one. We use the unit of the radioactivity as the specific activity. That means now you are going to specify according to the weight of the sample. So that means the specific activity is used to specify the fraction of the radioactive nuclide present in inactive sample. What is the active? Active mean the radioactive sample present in inactive sample. So this is called the ratio between these two is called the specific activity, because it depends how much you have the sample, inactive sample, and in inactive sample how much is the active radioactive nuclide, because you are getting the radioactive out of the active nuclide or the radioactive nuclides. So how can you define this one? This is represented by the A. As A is the activity, as small is the specific activity. So this is simply obtained by dividing the total activity by the mass of sum of all the radioactive and the stable isotopes of the elements. So this is the actually the formula is given over here. Let's suppose if you want to measure the activity of the sodium activity in number of curies or the becquerel, it depends whatever you are going to use the unit. So here this is the important, that means the total number of grams or the micrograms or the nanograms, whatever it is, the total amount of the sodium. This is the it is the sum of the active and the non-active or the radioactive substance, uh, active and the inactive substance. So this is the total weight of the sample. In total weight, what would be the activity of the active sample? So this ratio is called the specific activity. And similarly, sometime because this is a simple sodium activity in total number of the gram of the sodium, but sometimes let's suppose this is a sodium carbonate. You are using the sodium carbonate as a source for the sodium 24 activity. So how can you get the specific activity? Simply, this is the number of becquerels or the curies of the sodium activity divided by the now the number of micrograms or the grams or whatever it is the weight of the sodium carbonate. So important over here is you have to take the total number of the weight of the sample in which you are going to get the activity of the radioactive nuclide. So this is the all about the units and the half-life of the radioactivity. This is the graph which is showing you some of the specific activities of some carriers, free radioisotopes, and these are the some of the radioisotopes are given over here. These are the half-life, and this is the actually the unit is going to give you the indication that this is the specific activity. So this is the curie per gram of the isotope. That means the activity curie per gram of all these of the isotopes, radioisotope, that is going to give you the radioactivity. So it doesn't matter how much is the half-life. Sometimes half-life is large and the activity is small, and sometimes this relation may be reversed to each other. But this will give you the idea actually what would be the appropriate use of these radioisotopes, because at the last of the course we will be using these radioactive isotopes for some specific applications. So half-life is important, because if you want to get your results uh, within a specific time, then you have to decide which nuclide would be the appropriate to be used, not having the short half-life or not having too much half-life. It depends on the application, and its activity is important, because this also gives you the idea for specific applications of the radioactive nuclides. And this is actually the gram of the isotope in 1 microcurie. So this is the reverse of to this one. Actually, if you want to get this value, just first to convert into the microcurie. So this would be the 2.2 exponent 7. Now multiply by exponent 6. That will give you the microcurie per gram. And when you reverse this one, 1 divided by all these factors, this will give you the value of this 4.7 exponent minus 14. This is the gram per microcurie. So this is just the reverse of this 1 gram. This will give you the idea that in this activity, what gram of the isotope would be required for this type of the for this value of the activity. So this is the table. Just as a reference you can use to select your radioactive isotope for a specific applications.